Okay, welcome back. Maybe let me start with a, a quick correction over here. Of course, this is not pi over 2 or pi over 6. This is just pi over 3. Okay, so as we discuss over here, this is exactly the same value. Okay, I'm sorry. Okay, fine. So this is a correction. Now the next problem. Actually we have a similar kind of problem. Now we are going to express as before the volume of the region R, and the region R is defined like this. So let's try to understand. It's bounded by this equation, basically this one. But this really corresponds to this the orange one, right? This is just a cylinder actually. And also we have another tank which is here, and the second one is the blue one, right? This, I mean, maybe I should use the corresponding colors maybe. So this is the blue one, okay, and the first one is the orange one. Okay, I don't know, I have some orange thing. Okay, fine. Okay, fine, I'm sorry. Okay, you understand. Okay, fine. Anyway, so, but of course we have a symmetric picture. I mean, this is just one part of the picture. I mean, let me say this is just one part, so the R plus part, and we have some R minus part. So we have exactly the same picture, right? On the actually other part of in the part in this which we are not seeing clearly, but we have another part on the bottom, right, on the below part of this coordinate axis in the minus z direction. Actually, we can easily observe that. Just first focus on, as we did before, the curve of intersection and try to understand the base region, right? So let's try to understand the base region. As you see, we have a kind of a circular shape over here, which is not a coincidence actually. And actually we have a similar kind of picture over here, right, on the bottom. So this is the upper part of the picture, and we have a below part, basically. Okay, fine. So let's try to understand this thing, and you can easily observe that. So over here, maybe I should write it down like this. This is just, we don't need that part. Okay, something like this. So let's try to solve them at the same time, right? So we have x squared plus y squared plus z squared equals 2, the boundary term. And this turns out to be, if you really want to understand the intersection, just use this property, solve the equations at the same time, right? The usual trick. And we have this, therefore we have exactly z equals plus minus 1. Therefore the first yellow circle is exactly lies in this plane, right? This is exactly z equals plus. And we have another actually on the bottom part, right? Something like this, if you like. So we have another plane, z equals minus 1, and we have another circle like this. Okay, therefore the curve of intersection is just a circle. So the curves, if you like, the curves of intersection are just are circles, which is given like this: x squared plus y squared equals 1, lying on z equals 1 and z equals minus 1 respectively. Okay, therefore one circle lies on this plane, z equals 1, the yellow circle, and the other one is actually in the plane z equals minus 1. So everything is fine. Therefore, due to the symmetry symmetry of the picture, it is enough to study, right, the R plus, okay, the upper part. Therefore, the R plus is just the region. So as you see, maybe once more, actually we have this base region over here. Actually, you can easily observe, right? We have this base region, and we have this, I mean, after this intersection, you see this will be, I mean, this part plus this part will be our region on this base region. Therefore, the picture is, if you like, the picture is something like this. So we have a cap like this, okay, and we have a cylinder. Now this part is included. Okay, this is the base region. So this part and that part is now included. So the whole picture is R plus. Okay, and with, of course, with the base region, maybe I should use something like this. So with the base region, which is just a disk, unit disk. Okay, this is the base region D, and the D is just the unit disk. Okay. So these are the pictures basically, and it's enough to compute, actually it's enough to evaluate the volume of R plus, and therefore due to the symmetry we are just going to multiply by 2. That's all. Fine, so let's see how to compute. As before, we need to be careful. Why is that so? Because as we discussed before, so maybe I should copy this thing, and so I have something like this, but now since we are going to use the spherical coordinates, we should be careful, right? If you remember, so therefore we have this axis, and with that one and this one, right? If you like, I mean, it's not a good picture, but anyway. Fine, so we have this, and we just introduce our spherical coordinate system as before. So rho sine phi cosine theta, y will be rho sine phi sine theta, and the z will be as before rho cosine phi. Okay, and with this volume element, rho square sine phi d rho d phi d theta. Okay, fine. So let's see. So we have such a picture. Now, as before, we throw some rays, right? So this was the deal. So we throw a ray, oops, like this, and it hits that point. So everything is fine. This is our ray, and we have some angle phi, so we have some corresponding angle on the bottom, so we have an angle theta. So everything is fine. But the problem is, what if we keep throwing rays, for instance, that one, no problem. So that one, no problem. That one, no problem. But until we hit, for instance, this point, no problem, this point, no problem, but until we hit exactly the curve of intersection over here, right, this one. Now we hit the curve of intersection, so we have some distance over here. So remember, this is 1, so we have a unit sphere, so this is 1. Therefore, this specific ray, right, at some specific angle theta, I mean theta actually, right, we have a full turn as before. It's not a big deal. But now, this specific phi, this is exactly when you can easily see. So this much angle can be attained since this is 1, this part is 1. This is exactly when theta is pi over 4. So as before, this is a specific angle. After this angle, behavior or the types of the point at which your light beam hits the surface or the part of the surface will be changed, because when you hit some other, this is the first light beam, if you remember, it hits the point and you change it. But now after this highlighted one, if you throw a ray, now it hits. So maybe I should use some other color. Now after you send a light beam, now it hits some point, the green one, and leaves the region, right? This is exactly the terminal point where your light beam hits the region. This is exactly where the red one light beam hits the region. But now the problem is this green one, the green point, let's say the point P, is actually satisfy different type of equation, right? So your light beam meets the surface at different types of points. So after that angle, as before, we discussed this before, after this angle, right, the ray meets the surface at different types of points. Okay, so this was the idea, if you remember. But now what type of points we have? The green one. But the green one, this is this is on the cylinder, right? So this is on the cylinder. So what does it mean in this new coordinate system? So the cylinder is given like this, right? We have a free z coordinates and blah blah. This is a cylinder. But with this new coordinate system, so when we employ these new language, and this left hand side is just the rho square sine square phi equals 1. And what does it tell us? So this tells us that this is exactly when rho equals 1 over sine phi. Remember, rho is in this case a positive number. So what does it tell us? When your light beam, if you like, the green one, hits the part of the surface, so this is exactly the part of surface when rho is given by this expression. Okay? So what about the red one? So red one is easy, because this is exactly, the cap one corresponds to the part of the sphere. Therefore, the equation is just x squared plus y squared plus z squared equals 1. So the points lives on that surface, therefore it satisfies the corresponding equation, right? That was the deal. But now in this new language, this turns out to be rho equals 1. And that's all, basically, right? Oh, no, what was the equation? Oh, not this was not a unit one, right? I'm so sorry. So we have this light beam, right? This was 2, right? In the question, this is not a unit sphere. I'm sorry. So this is 2. So this corresponds to rho equals square root 2. Okay. So what does it tell us, basically? And of course, what is the maximum range for the angle phi? No, this is not that much hard, I guess. Maybe I should use something. I don't know which color should I use. Okay, we start with this axis actually. This one, this is exactly when phi equals 0. But as you see, as the angle, I mean, as you rotate your beam, your angle phi getting larger, and then the final step is this. Actually, after this point, I mean, it moves like that and ends here. So this is exactly when phi is pi over 2. But on the other hand, of course, we have some theta angle here, but since we have a whole disk over here, so this theta angle is just has some full turn, right? So so we have a kind of a full turn over here. Therefore, I mean, this thing is turned like this and goes like that and finished. Therefore, really theta starts from 0 and the theta ends with 2 pi. You have a full turn on the bottom. Okay? So let us summarize. So let me collect all those information into a suitable expression. I mean the triple integral. So let's try to wrap things up. Therefore, the whole volume. Okay. So in total we have. So after this long discussion, in total we get the following. So we were trying to understand the volume of R, but I mean, remember, this is just something like this, 1 times dV. But what we observe, instead of the whole region, we just, using the symmetry, we just want to compute the half of it, the upper part, right? 1 times dV. Remember. And now by using iteration, we use some coordinate. Maybe I should use some extra space over here. So we have 2 times. Now how should we write down the integral? As we discussed, we should decompose our integral, right? So we have because we have a kind of a critical angle over here, right? Therefore, we should decompose our integral. So we cannot write down everything in a single integral. So let us try to be more careful. So let me start with this iterated integral, which is just, I mean, this part is standard. So this is not the deal. But as we discussed, so we have a kind of a critical angle, which is pi over 4. Okay, pi over 4. So up until pi over 4, so our rho, remember the green, remember which part? Okay, red discussion. Okay, the red light beam. Okay, so we have a kind of a red light beams until we reach the angle pi over 4. Therefore, maximum rho you can have is just a square root 2. And therefore, actually, rho changes from 0 to square root 2. And on the other hand, I mean, the theta part is just, you have a full turn, so you have 0 to 2 pi. The range is clear, no problem, because on the bottom we have just a whole disk. And we really want to scan everything, therefore we need a whole rotation. Therefore, the range is 0 to 2 pi. And plus, this is not the whole story, right? So plus, after we pass, right? After we pass this critical angle, I mean, this is not a terminology. I mean, this is something, I mean this important angle. I try to highlight the importance of this angle. So after this critical angle, pi over 4, until we reach, I mean, the which one? The maximum value, phi can take pi over 2, okay, pi over 2. But now we have another types of light beams, if you like, the green one. Now rho starts from again 0 and it hits, okay, just let me erase this p, I mean, it may confuse. And now it hits the surface at this green point, but the green point, when you hit the surface, it really corresponds to value when rho equal to that one, this expression. Therefore, this is exactly when 0 to the row reach actually this sort of value. Okay, and what about the rest? I mean, rest is easy because it's 0 to 2 pi, nothing new, but this part is again standard. Okay, something like this, d rho, d phi, d theta, and that's all. Okay, as I said, as you see, we need to decompose our integral into two pieces. Most important part is this critical angle actually, right? Because after this angle, exactly, I mean, the point your light beam hits the region actually is, I mean, they are expressed by different equations. Okay, this is the reason. So the green points lies on the cylinder actually, and the red points lies on the sphere. Therefore, their correspondence with the rho are different. Okay, therefore you should compute this correspondence carefully. This is the reason why we have two we have such decomposition. So we have two triple integral basically. Okay, fine. So if you compute this, I mean, this is the expression basically. I mean, we only compute the upper part, but for the lower part, we just multiply by 2. And this triple integral in spherical coordinates really express the volume of this region of interest. Okay, fine. So this is a kind of a long journey, right? So as you see, I mean, we should be careful while computing or expressing those things. Okay, fine. Maybe before close this section, as before, I have some exercises. Actually, by using similar ideas that we have already done throughout the session. This was a long session, I'm sorry, but I guess so these are nice exercises. You can check them. Okay, so thanks. So see you next time.